Okay. Okay, so we will start. So am I audible? Okay. Yeah. Thank you. Okay. Yeah. So good evening, everyone. So welcome to the sixth session on exploring nonlinear dynamics from the basics to applications. So till now we have covered different chapters in the nonlinear dynamics, and now in this lecture we will look into the chapter on limit cycles. So we will see what are limit cycles. So there was some pending on the index theory that we will cover in the first half of this session, and then we will go to the limit cycles and we will see how are limit cycles important and all. So these are some of the references and videos you can refer to. Yeah, so we will begin with our session now. So I will just yeah. Yeah. So till now we have seen linearization of a system. Which we used to remove the higher order terms and we used to do the linearization of a system about a fixed point. So this is important. So about a fixed point is what we were used to do till now. So if you remember, we did both in 1D and 2D. We have done this where we used to give a perturbation eta in 1D, and in 2D we used to say it as u, which is nothing but x minus x star, and we used to see how this emerges out. Will it grow or will it decay? That was our main concept. And so this was till now we were all looking at the linearization of a system about a fixed point. So if you look at the linearization point, it is actually a local method wherein you are you have a fixed point and you have a localized region around. We were completely looking around this region and we were checking whether the perturbation will grow or will it decay. That was our linearization method, and this was a local method where locally near to the fixed point all the theories will work. Now we try to see in a global picture. So we try to get a global information about the phase portrait. We will try to see can we get a global picture of the system. So in order to answer, so there are certain questions like, will a closed trajectory always enclose a fixed point? Or say you have a fixed point and will there be a trajectory every time? That's what we saw in a centers where you have a closed circle every time revolving around a fixed point. Are these every time they are present in near the system, or will they have any bifurcations from one state to the other state? Will they show something like that? So these are all, when t tends to infinity, we don't know how the system will behave. Not near to the fixed point, but very far from the fixed point, how the system will behave. If your initial conditions are starting far from the fixed point, then how will the system behave? We can't use the linearization theory. So for that, we use a concept called index of a closed curve. So this has certain limitations. We will go through that also. So what we will be discussing now is called some index of a closed curve. So index, say you have a curve C somewhat like this. So the index of a closed curve C is an integer. So definition is important, that's why I am just mentioning this here and writing it. So it's an integer that measures the winding of the vector field. So we will discuss what they mean by winding of the vector field. Winding of the vector field on C. So say you have a curve C like this, and so it does not need to be any trajectory of the system. It can be say you have different vector fields which are spread over like this in the system. So we are just connecting the loops. We are just trying to connect all the vector fields and just draw a loop around it. So it need not be a trajectory of the system also, because if you are saying that it's a trajectory of a system, then your tangential to your direction is what your velocity component will be going. So it need not be in this case it need not be. We are saying a general case. So say you have a point x comma y, then this vector field will give you x dot comma y dot of the system. Then if you say take a reference of the horizontal axis, then you will have an angle which is made by that vector field. Now this looks something similar to what you may have, if you have learned about the electromagnetism and all, you may have seen something like this, where you have a surface. You usually take a surface over a sphere and you say that the static charge that is inside this surface can be found out by the field that is present over this surface. So something similar to that analogy, here we try to use this index theory concept. So here say you have a equation of the form x dot is equal to f of x, and say f of x is some smooth vector field. It's a smooth vector field on the face plane. So this yes, yeah, I am hearing. No. So the closed curve need not be touching the same points actually. We are just trying to join the different vector fields, and we are trying to just draw a loop. Here it need not be it's just a loop which does not cross over each other. It can. So we are initially starting with the general case. Then we will see if it is a trajectory. When you are connecting all the vector fields, how the system index will behave, we will see in the step. Yeah. So if you have a equation of the form x dot is equal to f of x, and say f of x is smooth vector field. This smooth vector field we are saying so that it's continuous over the field, and there is no discontinuity across the path where the trajectory is moving. And now, so we consider this loop and we say that it's a closed curve. It does not intersect over each other. Then if you have this, so we take a point x comma y, then corresponding to that the vector field which we have just seen. So if we take this particular vector field, x comma y, so then you have, say I will just draw a zoomed version of it. So you have a phi angle that is made by this vector x dot comma y dot. So with reference to this horizontal axis, this vector field will make an angle phi. So the angle phi can be represented by nothing but the slope of this. So phi is nothing but tan inverse of y dot by x dot. Now in this theory, what the concept we take is, so you are taking a vector field, say this is the first vector field, that is say x. Now this x moves along the curve C. So this is your curve C. So if I draw the full diagram, so this was our curve C and this was our first vector. This vector field moves along this curve like this. Now we focus on this each vector field x1, x2 and go on. Now we see that so our standard procedure is you move in the counterclockwise direction, and the angle phi changes continuously since the vector field is a smooth. We have said that f of x is a smooth function, so the angle phi will also be moving smoothly. So it will go like this actually. So when x returns to the starting place, if you are starting here and if it returns to the back, then you are actually completing a 2 pi revolution. So I hope you got the concept. So you just take a vector field and you take the initial phi as with reference to the horizontal axis, take an angle phi, and you go to the next each consecutive vector fields and see how that angle is changing. We will do an example so that you will understand more. So the angle, that total angle that is covered, or we say the net change in phi direction, phi over one circuit, is what we represent by this phi of c. Now the index of a closed curve is closed curve c is defined as I of c is equal to 1 by 2 pi. So if you are completing one revolution, you will be getting an of phi c. So if you are completing a 2 pi degrees of revolution, then you will get an IC of 1. So that is the index of that closed curve. So IC is the net number of clockwise revolutions made by the vector field as x moves counterclockwise around c. So it is the number of counterclockwise revolutions made by the vector field. So here, in order to keep a convection for the sign, we take x moves in the counterclockwise direction. Once in counterclockwise around c. So we'll just do an example to find how to find an index of a closed curve. So say you have a curve like this, say it is c, and you have different vector fields given to you. So these are the different vector fields we given to you. Now we need to find the index of this closed curve. So what we need to do is, so we need to check our first step should be check in the counterclockwise direction how the vector field direction is changing. Direction phi, how it evolves. So for that, what we can do is we take this as the first. So this can be any point you can take, but we generally take this as one and we go counterclockwise. So this is your second, third, fourth, fifth, say sixth, seventh and eighth. Now you have the different vector fields. So say this is your point, say some point, center point, and if you take one, it makes 0 angle with the horizontal. So its phi is 0 now. Now if you take the second arrow, second vector field, it is going downward like this. So this is your 1 and this is your 2. And the third is going like this. Similarly, fourth is going like this. Fifth is going like this. Sixth goes like this. Seventh is like this. And eighth is like this. Now if you look at it, from 1 to 8 we are covering a counterclockwise direction and we are reaching back. We are starting here and we are reaching back here. So our phi c which is making is 2 pi. So the index of the closed curve is nothing but 1 by 2 pi times phi of c. So this is nothing but 1 by 2 pi times of 2 pi, which is nothing but plus 1. So this is how you calculate the index of a closed curve. We will see. So did you guys get how to calculate the index of a closed curve? Yeah. So this, yes, there is a possibility of. Now we are, that's plus and minus we are keeping. That's why I specifically said that we keep standard as counterclockwise as the positive. Now if you are moving in the clockwise direction, it will be in minus. So in order to specify that direction, we are mentioning +1 and -1. Yeah. No, anti-clockwise is positive, clockwise is negative. Yeah. So we will do one more example. We will see. So you, every time you do not cover whole 2 pi radian. So we will see one more example where, say you have one more curve like this, and now this time you have 1 here, 2 moving like this, 3 like this, 4, 5, 6, 7 and 8 is in this direction. Now we need to find the index for this point. So for that you take a initial point like this, and initial one, it makes 0 angle with the horizontal, then the second makes like this, third is downward, fourth moves like this, and fifth, if you see, it is in this direction, sixth moves in this way, seventh in this direction, and eighth in this direction. Now if you look 1 to 8, if you want to go, you should be going in the clockwise direction. So our phi of C is nothing but -2 pi. So your net index will be times phi of C, which is nothing but 1 by 2 pi times -2 pi is -1. So now you have moved in a clockwise direction. So that's why we specifically mentioned +1 and -1. Now if you are not given these kind of vector fields, then how to see if your system is moving in having an index of +1 and -1? So we will say what is the significance of having a index for a closed curve. Within a few minutes we will say that. First we will just see how to calculate an index, then we will see its physical significance and all. So say you are having a equation for this vector field, x dot is equal to x square y and y dot is equal to x square minus y square. Now say it is on a unit circle is given of equal to 1. Now we need to find the index for this particular vector field. So x dot you know and y dot you know. So now we ourselves need to draw the vector field. So in order to do that, we first take this vector x dot y dot is nothing but x square y, x square minus y square. Now since it's given a unit circle, so you can draw a circle of 1, a radius of 1 you can take. Now we will start from this point here. So in order to start from this, your x comma y, that is nothing but your x dot y dot should be, x should be 0, y should have some value. So in that case, since it's a unit circle, we are taking 0 comma 1 we are just taking, so that you will be on this circle. Now if you are having x comma y, x dot comma y dot, where x comma y is 0 comma 1, if this is the condition, then x dot comma y dot will be, so x0 means this will become 0 and this will become -1. So if you look, so x0 and y1, x dot y dot will be x0 and y will be okay. So x y dot will be -1. So -1 is in this direction. Similarly, you can take different points on this curve and plot the x dot y dot values. Now you will have certain vector fields for this curve. And now you can use the same method. You take a point and plot the curve according to this, and you can see how the angle changes. From that you can get the index of this curve. So I didn't solve it. You can take minimum 4 or 6 points to get the index of this curve. So I have not completed it. So you can take different points and you can see how this system completes that point. But our important point to note is there are certain properties for this index. So if you are not given a vector field also, you can draw the vector fields and you can find how the system behaves. Apart from that, you can, if vector field is given, you can find the index directly. Now what are the properties of an index is, so say you have a curve C which is continuously deformed. It is continuously deformed to some other curve called C dash. It's a closed curve again. Main condition is without passing through a fixed point. So we are saying that if it does not pass through any fixed point, if you have a curve C and it shrinks and shrinks, it goes and goes, and finally you reach some C dash without passing any closed curve, without passing any fixed point, then the index of this curve will be equal to the index of the new shrink curve. So proving that it is nothing but if you are having a fixed point, say somewhere here, since it's a continuous function, it should be a scalar. It's a single valued function, so it should be continuous, because we said that f of x is a continuous function. It should be a constant value. If you are having a fixed point somewhere here, your curve will immediately show a jump in the value. So this jump in the value will not be there if you are not crossing any fixed point. So if you are having a closed curve C and if you are not crossing any fixed point, but your curve is slowly getting shrinked and finally you reach some point C dash, then the index of that big curve and the shrinked curve IC dash will remain same. So that's the first property. And the second one is, if C does not enclose any fixed point, if it does not enclose any fixed point, then the index of this curve is equal to 0. So that means, so this can be detected from the first point itself. Say you had a curve C and it is shrinking to another small curves, and as it shrinks down, if it doesn't have any fixed point, it will go very low and all the vectors vector field will be aligned in a parallel direction. So that means your final index will be going to 0. So that's why we say that if C does not have any fixed point within it, then your index of the closed curve will go to 0. So this is the second property. And the third one is, if we reverse the direction of the vector fields, reverse all the arrows or direction of the vector fields, say by changing, this can be done if you are changing the arrow t to minus t, if you are reverting it, then you can see that the index remains same. Index is unchanged. So this can be simply said directly, because if you are having an arrow like this and if all the arrows are going back, then the net IC will be is nothing but, since it is 1 by 2 pi of phi c, this phi c will remain nearly same for both the cases, only the arrows are changed. So the closed curve, for that closed curve, the index remains same. And the last property of an index of a closed curve is, now the closed curve which we have assumed is a trajectory of the system through the path through which our phase fluid or an imaginary particle moves. If that trajectory of a system it is, then see, if you are having, then the vector fields will be tangential to these points. Any point on the trajectory, if you want to get the x dot value on that, you just need to draw a tangential to the trajectory of the system. So these are the vector fields now. Now if you see the curves, you can see that this actually rotates and it covers a 2 pi value. So that means if your C is a trajectory of the system, then the index of that system will be every time +1. So this can be directly seen from the curve from the diagram itself, because if you are having a trajectory, then all the vector fields will be tangential, and when you are drawing, you will eventually, because you will not have two velocities at a particular point, so you will eventually close down to 2 pi radians. So yeah, so these are the 4 properties of the index of a closed curve. Now there is one more point. So we saw in the previous lectures, we have stable node, unstable nodes, and we had saddle nodes. When you are solving the problem, when you are getting a fixed points, when in a 2D you can get stable node, unstable node, saddle nodes and all. So if you are having a stable node, what is the index of that curve? So say if your C is a trajectory, so in a stable node, all the points will be coming to your point. So this is nothing but this is equivalent to the first example which we saw. All the points which are coming towards a point. So for that, the index is nothing but +1. Similarly, for an unstable node where your point is here and all the points are moving away from that fixed point, it's an unstable node. And so we will just draw this, and so we will just draw this, and this is the curve you will have. So if you put 1, 2, 3, 4, you will turn up and you will have a 2 pi. So your index will be +1. Similarly, for an unstable node, all this will be moving out, and if you take this as 1, 2, 3, 4, so you have 1 over here, so 2 moves here, 3 moves here, and 4 moves out. So now also you are again coming back to this 2 pi. So for an unstable node or a stable node, your index of the closed curve is +1. So index of the closed curve has a limitation that it can't tell anything about the stability of the system. Either is the stability of the system, it can't differentiate. So for finding the stability, we need to do other analysis. Whereas if you look at the saddle node, so saddle node is nothing but you have one curve coming towards it and one curve going outwards. Now if in that case, if you look, so this is 1, 2, 3, 4 if you fix. So this is our 1, 2, and this is our 3, and this goes to 4. So now to go to 4, you need to cover like this. So this covers a clockwise direction. So phi c is nothing but -2 pi, and your index is -1. So now you can, from all the nodes, you can differentiate a saddle node using the index of the closed curve. So not only all the saddle nodes and stable and unstable nodes we know, we also came across fixed points like spirals, centers, and degenerate nodes also we came across. So these all fixed points also, they also show the index of the curve as +1 only. So only one different species that shows, or fixed point that shows the Difference is only the saddle node, which has a index of -1. Now, so is that clear up to this point? Are there any questions? Yeah. So we will see the application of that within 1 or 2 examples. We will see the application also. So now, so there is one small theorem, or you can just, to finish this fixed point concept, we need to just know if you are having a, so there may be a conditions where, say, you have a closed curve C, and inside that you have different number of fixed points. So since the C is a closed curve and it surrounds an n number of fixed points, say 1, 2, it has n number of fixed points inside that closed curve, then how will you find the index of that closed curve is the question. So that is being discussed in this particular theorem. So in this, we need to find the index of the closed curve with respect to the index of each of these fixed points. So say I will write it as ik. So the theorem says that the sum of the indexes of the total number of fixed points will give you the index of the closed curve, the total closed curve. So we will just see how that is possible. So we will just say initial, our step 1, say you had a closed curve C and in that you had fixed points. Now these fixed points, for each fixed point you can draw a curve like this around it, so that it will closed curve around it. This C curve you can shrink slowly to this kind of slope. So you should not touch the fixed point, because if you are touching the fixed point you will have a discontinuity. So this C curve now shrinks to a small curve like this, and this is the branch that connects to that. So this C curve now it shrinks to this kind of C dash, and we know that from the first point, closed curve and the shrinked closed curve will have the same index. So till the point where you don't touch the fixed point. And now you need to calculate, we are trying to find is the total index of the curve, total index of the closed curve. In order to do that, now we need to find the index for each particular fixed point and what is the index for these branches. Now if you look at the branches carefully, all of them are moving forward and backward. So there is a symmetry, and if you take them, they will cancel out each other. So now the angle which is remaining to be measured, okay, sure. So I will, yeah, sure, I will explain. So say, so our aim is, you have a curve C and it has n fixed points inside it. Now we need to find the index of this closed curve. That is our aim. So if you didn't have any fixed points, then you can directly go to the vector field and you can draw the plots and you can directly find the index of that curve. But now if you are having a fixed point inside the curve, how to find the index of that curve is the question. So in order to do that, we take a, say we have a curve C and we consider some 4 fixed points inside this system, and now we are slowly shrinking this curve C such that we don't cross the fixed points, because our theory says that if you are crossing a fixed point, there will be a discontinuity in the index values. So we don't have the theory to tell when you are having a discontinuity. We have learned only that till the point you have fixed point, you know how to calculate the index of the system. So what we do is, we slowly shrink this curve, slowly we will shrink this, we will move inside this curve slowly, It's like you have a lot of air inside this balloon and you are slowly taking out the air, sucking out the air. So now across these 4 points, the curve will look like this. And in this region, you will have some very thin bridge that is connecting all this thing, because it's all a single curve. So say this is our new C dash. Now we need to find the index of this thing. So you can draw the vector field on each of these curves and draw that and find the total index of the curve. But since this bridge, whatever we are seeing, these arrows are having, one is going like this and the other is going like this. So if you sum it up, all the fixed points values, if you sum it up, this bridges values will not be necessary, because anyway they are, one is moving in the positive, one is moving in the negative direction. So they will neutralize out. So one is plus 1 means other is minus 1. So you don't need to calculate the bridge values. Only you need to calculate the phi change across the fixed points. How the vector field is changing across these fixed points is enough to tell what is the total index of the closed curve. So from the definition we know 1 by 2 pi times phi of c. This is the index of a closed curve. Now here we know the angle only. What is the angle phi of c the vector field covers, we know. So you know only phi of c, which is nothing but 2 pi times IC. So now say these are 5, say I just mark it with tau something. So this will be of tau to differentiate what the original curve and the new one. Now this is the one known thing now. So we need to find the, we say that the total new curve is nothing but index will be 1 by 2 pi times phi of tau. This phi of tau, if you are having n number of fixed points, then it will be a summation of that. I equal to 1 to n phi of tau n, it will, because you have n fixed points like that. But this phi of n is nothing but whatever the 2 pi we have from this I equal to 1, phi of c is nothing but from 1, 2 pi times the index of the each fixed point. So sorry, this is n, we will write n. So this means the index of the reduced curve is nothing but the summation of the index of the each fixed point. So if your total curve will be nothing but I1 plus I2 plus I3 plus I4. So you just need to find, so we just, before this we told for a saddle node what is the index, for a closed, for an unstable node what is the index, for a saddle node what is the index we have seen, and we have similarly seen for a spiral centers degenerate nodes what is the index. Now from the previous classes we know how to find the fixed point of a system. Now if you determine the fixed point of a system, then you can find the global picture. In globally how the system, say you have a closed curve for all the fixed points, then how the index of that closed curve will be. That is nothing but the summation of each fixed point's index. So this index will tell you, can you have a closed orbit or not around that fixed point. That's the main physical significance of finding a fixed point for a closed curve. So if your index is plus 1, we mean is that you have a closed curve around your fixed point that is moving in the counterclockwise direction. Now, so you will have a question saying, why are we interested in these kind of closed curves? So physically, these kind of closed curves in nonlinear dynamics, they represent the periodic oscillations. So we previously saw there was a spring mass system, and when the spring is having a oscillation, a periodic oscillation, you will have something like sinusoidal waves being created like this. That is actual time series when you see. But in a nonlinear perspective, this starts somewhere in this point and it goes, it comes back and it goes again on the same curve. So these kind of closed curves, if you are observing in dynamical system, that represents a periodic oscillation. And lot of systems, they exhibit periodic oscillations due to external forcing or due to self-excited conditions also. They maintain these kind of periodic oscillations. So it's important for us to understand, do we have a closed orbit or not? In order to find that, if you find the index of a given arbitrary curve, if you take, and if you find the index and you get it is +1 and -1, then you can say yes, it has a closed curve. So there is some periodic oscillations the system can behave over a t tends to infinity. It can behave in a periodic way also. So that's the whole idea why we are finding the index of a closed curve. So is that clear? Or I will just show you one example. I will just show you one example which we have looked previously. Then you will understand how you can relate it to the actual physical things. Before that, yeah, so there is one more small theorem before that we can note. It's like, if you have any closed orbit in the phase plane, it must enclose fixed points. So I will just write it down. So if there are any closed orbit in the phase plane, must enclose fixed points, whose indices sum to +1. So this can be just found, say from the previous theorem we saw that if you have a closed curve, it is the summation of each of the fixed points indexes. Now if you sum it up from the, say if your C is a trajectory, we said that its indices will sum up to IC equal to +1, it will sum up. So that means your total index of the closed curve is a summation of this, which should be equal to +1. So this indirectly says something. If you have a closed curve and you have a fixed point inside it, then this fixed point never can be a saddle node. This is because if you have a saddle node, its index is -1, and this is not possible according to this theorem. So you can clearly eliminate out is if there is any saddle node possibility or not using this index theory. So that's one of the theorems that can be helpful. So I will just show you one example which we have looked previously. So it is that rabbit and sheep case which we looked. So in that, our question is, can there be any closed orbits? Or so if I just show you, you just revise what it was. So say you have rabbits over here and you have sheep over here. We found 4 different fixed points for that. We had one here and we had one here. So we found 4 fixed points, and we found that this was unstable and this was stable, and this was a saddle node and this was a stable node. And now in this phase plane diagram, can there be any closed orbits is our question, or can there be any periodic oscillations or periodic behavior, that is rabbits are increasing then decreasing, rabbits are increasing then decreasing, that kind of periodic behavior can we see for this condition is what our question is. So for that we will use index theory and we will directly say is it possible or not. So for that what we need to do, say consider you have a closed curve somewhere over here C. If you say your closed curve is C here, but you should have a fixed point inside it which should be summing up to +1. So here you don't have any fixed point inside it. So that means your curve cannot lie anywhere in this region. So the curve can lie any of the 4 points which I am showing here. So we will go with the first point here. So say you have a closed curve like this around the saddle point. But saddle point has a index of -1. And if you have a fixed point inside a closed curve and it sums up to -1, it is not possible according to the theorem, because IC should be summing up to +1 every time. So there can't be a closed curve here. Now if we go and check at the next point, say some here, if you do, so here if you see, this is a stable node, so its index should be summing up to +1. So that means this closed curve is possible. But there is one more problem here. If you look carefully, this fixed point, this stable node and this stable node, if you want to draw a closed curve, you need to cross the x-axis and y-axis of this thing. Actually, which one said? C1 is a unstable node, because you can't have negative rabbits and positive rabbits, sorry, negative sheep. You don't consider this part, only this part we consider. It's an unstable node, and in both this C1 and C3 case, you will see that for you to close the curve, you need to cross this x-axis and y-axis. Actually, the x-axis and y-axis are also a trajectory of the system, where you have different points actually. So there is a rule that trajectories will not cross over each other. This is because, as I mentioned in the previous class, if your trajectory is crossing over each other, at this point your particle will not able to, it will be in confusion state, whether to go in this state or in this route. So we say that never in the 2D non-dynamical system equation, trajectories will never cross over each other. So for that, if you look at that condition, then C1 and C3 is also not possible. Then if you look at C4 also, the same condition applies here also. For it to become a closed curve, it needs to cross the same. So in net result, we can say that there cannot be any closed orbit or any periodic solution in the rabbits versus sheep case. So there is no case where periodically the sheep and rabbits will come up and down. That kind of cases is not possible. So that's one of the application of index theory, how you can correlate and say is there any periodic oscillations or periodic conditions can be brought to the system or not. And you directly found it. You didn't do any analytical or anything. We just found the index values and we directly said is the closed orbit possible or not. So this is the application which I wanted to explain. So are there any questions? Yeah. So that's what I mentioned here. So if you are having a closed orbit, you will have something like a periodic solution. You are starting from certain point and you come back to the same point. That's a closed orbit. So that kind of solutions, are they possible? In rabbit sheep case, you can't do an experiment or you can't do the model and check all this. But this theory can help tell you is there any periodic kind of oscillations possible, because you know that there are mainly 4 fixed points for this system, and we analyzed that fixed points and we came to know that there cannot be any periodic oscillation state possible in that system. So circle in a dynamical system theory means you are starting from somewhere and you are coming back to that same point. So these are very important, and we will next discuss something known as limit cycle. So there are a lot of some points where we call limit cycle oscillations. These are periodic oscillations we actually mean by. So these kind of periodic oscillations, if you are building up, say in the case of a rocket engine, if you consider, if these kind of periodic oscillations, if they build up, your actually rocket engine will blast off, because these periodic oscillations cannot be withstood by the chamber. Similarly, if you are considering in a circuit or any of the oscillation in the fluttering of a air wing and all these things, your airplane has a wing and that will flutter up and down, up and down. This is also a periodic oscillation. But in actual scenario, if these kind of oscillations comes when you are in a flight, this is very dangerous, because your fluttering wings will now be damaged very fast. So it's very important to study these kind of periodic oscillations, and people use this dynamical systems theory to analyze how will the system will go to these kind of dynamical oscillations or not. That's the significance of this circular or finding an index theory or a periodic oscillation theory. Yeah, well, did I answer that, or I answered very... Okay. Okay, so we will move on to the next topic, which is, as I mentioned, called limit cycles. So there is a standard definition for limit cycle. A closed curve and a limit cycle are different. A closed curve and a limit cycle are different. So in a limit cycle, the definition of it is a limit cycle is a isolated closed trajectory. So this is very important. So it should be an isolated closed trajectory. So by isolated we mean is that any nearby trajectories are not closed, either they spiral towards or away from the limit cycle. So by that what I mean is, say you have a closed curve like this, and if it for it to be a limit cycle, all the curves that are starting nearby, it should not be closed, either it should come towards this or it should go away from this closed curve. If such a closed curve exists, such an isolated closed curve, if it exists, closed curve if it exists, then this is called a limit cycle. On the contrary, if you are having a closed curve, so we saw centers. So these centers are closed curves, they are not limit cycles, because near to this region, if any point if starts here, it will be thrown out to this closed curve. But in a limit cycle, anywhere you start, if you are having a stable limit cycle over here, your curve will eventually come to this limit cycle only. It will not go to any other closed curve. So that's the importance of this isolated closed curve. That's why we are stressing more on that isolated term. So there can be three different kinds of limit cycles actually. So say you have a closed curve like this, and any curve that starts somewhere here, if it goes and it tries to come to this closed curve, and anything that starts inside also will try to move, and it will try to move towards this closed curve, then we call this as a stable limit cycle. Because as t tends to infinity, every point anywhere you start, you are eventually coming to this closed curve. And as I mentioned, closed curves means periodic oscillation. In real life engines or any of these systems, if you see, most of the model systems, they exhibit what we call self-sustained oscillations. So apart from giving an external forcing and making the system to oscillate, within the system, due to the dynamics of the system, there will be self-sustained oscillations maintained by the system. So For example, there is a rhythm in the human body temperature which is maintained by the body. So there is a periodic oscillation that is being maintained by the body to keep our temperature up and down within a particular range. Or some other examples like some of the chemical reactions. If you see some of the chemical reactions in YouTube, you will see that it will be initially blue, then it will suddenly go to green, and it will come back to blue. So these kind of blue green oscillations you can see in certain chemical reactions. So in the future thing we will see what are some chemical reactions which shows this. So these kind of oscillations, so oscillation by mean it goes to certain state, comes back to a particular state, and it keeps on doing this with a time period t. If that is maintained, then we say it's a periodic oscillation, and that periodic oscillation is nothing but a closed orbit. And if it's an isolated closed orbit, we say it as a limit cycle oscillation. And apart from stable limit cycle, if you have a limit cycle which is, say this is your limit cycle, then you, if any of your curves, any curve that starts anywhere here, it tries to move out, or anywhere this starts, it will try to move towards an inward fixed point, then we call it as an unstable limit cycle. Similarly, there can be stable, as we said previously, there can be stable node, unstable node, and saddle node. Like that, here also you can have stable limit cycle, unstable limit cycle, and what we call half stable limit cycle. So if this is your limit cycle, so some curves which is starting here may try to come and go like towards the fixed limit cycle, whereas some which are starting here may try to go away from it. So some try to come in, some try to go out. If these kind of things are happening, then we call it as half stable limit cycle. So these are the basic different categories of limit cycle oscillations. So I hope you understood the difference between a closed curve and a limit cycle oscillation. So it's important because when you are going to draw the things, you should not be thinking that it's a closed curve or limit cycle, how to differentiate them. Okay. Yeah. So we will just look at a simple example of a limit cycle. So say you have so drawing a limit cycle is easier in polar coordinates, because if you know r and theta, you can directly draw the circle and you can imagine them very nicely. So we will take a simple example where r dot is equal to 1 minus r square is the one of the term, and theta dot equal to 1 is the next equation. Now these are the radial and angular dynamics which we are considering. If you consider this, if you find the fixed points, you can directly say, if you put it here 0, then at r equal to 0 you have a fixed point, r equal to plus or minus 1 you have a fixed point, and theta dot equal to 1 is, in the sense, it means you have a constant angular, so you have a circle. Theta dot equal to 1 is that the rate at which your theta is increasing is kept constant. So that means it's a constant value, you have a circle over like this. Now on this circle, if you see r into 1 minus r square is the equation. So you have a circle center point here, and you have, so we can show that in Desmos. So our idea is to see how the curve comes into the circle or not is our question. So if you look into the equation r into 1 minus r square, so it's nothing but r minus r cube. Now if you plot it here in the terms of r and theta is this direction, if you plot that, you will see that any point that you are taking outside r greater than 1, it will eventually try to come to this fixed circle, onto the circle. And similarly, anywhere you start, it will eventually try to move towards the limit cycle also. No, I didn't say limit cycle, I will just say towards this orbit. and so we need to check if every curve is going outside or is coming in. And similarly, if any point that starts here near to the 0, if it is, we see that it tries to move away from the fixed point, so it's an unstable point. So if you find the f dash of x value, if it is greater than 0, you can say it's an unstable or a stable fixed point. And so for this particular case, you can directly find the equation r dot is equal to r into 1 minus r square. If you consider since theta dot equal to 1 is a constant here, it's uncoupled now. So that means if you plot the r dot, now it's a 1D, you don't need to have any circle or anything. You have r and r dot. If you have r minus r cube equation, we know it is somewhat like this. This is nothing but our logistic equation, r into 1 minus n square, like this. So r minus r cube curve looks like this, and this is 0, this is plus 1, if you say plus 1 comma 0, and this is 0 comma 0 fixed point. So since it's positive, our arrow goes in this direction, and here since it's negative, it will come in this direction. So this is so this is actually a stable fixed point, and this is a unstable fixed point. So that's what we have seen from this r theta graph also. You circle any curve point that starts near to the 0 point, it will be thrown out to this unit circle, and anything that is starting outside will try to come towards the unit circle 1. That's why 1 is a stable point and the 0 is an unstable point. Now for clarity, if you draw the time series of this, say if x is equal to r cos theta, if you take, and you know the theta and r values at each point, you can draw the time series of this. And if you plot the time versus x graph for this, you will see that it's a cos wave, so it will go like this. So this periodic oscillation is what we are representing by this circular closed orbit. And we see that any point that starts outside or inside is trying to move towards that unit circle of 1. Unit circle. So that means this is a limit cycle. So that's what I wanted to stress here. So was that clear how to say if we are getting a curve and how to tell if it is a limit cycle or not? Okay. Okay, I think I will just give you 5 minutes break. If any questions is there, I can send. Else we will come back at 7:40. We can meet. Yeah. So we can take 4 minutes break and we will come back. Yeah. Okay, we will wait for 1 or 2 minutes. Okay. Yeah. So now we will look into one of the famous equation called Van der Pol equation, which is very famous in nonlinear dynamics. So this was the equation which historically, if you say the old radios and electrical circuits, they used to have this vacuum tube methodology, and these nonlinear electrical circuits, they exhibited behavior which this equation which was derived by Van der Pol. These nonlinear electronic circuits, they showed oscillations or periodic movement. They had certain oscillations when they are working. So these oscillations were replicable by this Van der Pol equation. So this model was able to show this dynamics actually. And the equation goes somewhat like this. It's like x, it's a second order equation with x double dot plus x square minus 1 into x dot plus x equal to 0. Yeah. Okay. Okay. So in this equation, this nu is actually a parameter. So this is what we actually change. Nu we change, it can be greater than or equal to 0. And this is a, so if you remove this term over here, which say if you remove this particular term, then you are left with only x double dot plus x equal to 0. This is just our simple harmonic oscillator which we have discussed. So this is nothing but a simple circle actually. Now when you are this additional term, when you are adding it up, it's the system now becomes a non-linear oscillator, it becomes. So that means this term is actually behaving like a damping term. Instead of the system remaining at a pure circle, now your system will slowly divert from that circle and it will try to go down to a particular fixed point. That is possible by this damping term, and this was the main finding, or this was able to show certain if you have a circle and eventually it will damp out due to friction or viscous or any of the effects, your oscillations will slowly die down, and this damping term is able to replicate that dynamics. That's why it was able to capture the actual dynamics which was shown by this nonlinear oscillators. And if you look carefully, the term, if your value of mod x is greater than 1, the term nu into x square minus 1, it will be positive and it gives a positive damping to the system. So if you have any high oscillations, it will slowly, it will try to go down like this. Whereas if your x values are less than 1, your whole thing will be going to very low values, because if you have 0.1 square is 0.001. So that means it will be very low value and it becomes negative, and a negative damping is made. Negative damping means you had some small oscillations, say you had something and it was dying down, but once it shifted to negative value, it started getting back up to higher oscillations. So based on your new values, your x and can go from positive to negative damping, and it can now show a oscillation which can be like this, it goes down and it can come up like this. So these kind of oscillations can be shown by the Van der Pol equation, and I will just show you how actual phase plane diagram, how it will look like, so that you will have a clear idea. Okay, before that I will, so from our first classes we know, if you have a second order equation of this form, x square minus 1 times minus 1 x dot plus x equal to 0, if you have a second order equation like this, in order to solve, we need to convert it into two first order equations. So what we usually do, we put, say, x dot is equal to some variable y. Oh, okay. So you had something like, yeah. Yes. So Van der Pol is famous for its limit cycles and how it can give a closed orbit, how its oscillation behave. And Van der Pol has additional features like different time scales it can show. So that's an interesting part in Van der Pol equation. And yeah, that's limit cycle oscillations. That's more important in Van der Pol's. This is the equation which you are able to show this kind of oscillations when you are having damping and positive and negative damping. That's the interesting part. It can grow and go down to a steady state and then can rise back also. Yes. So these are actually happening in real systems, and this model is able to capture these kind of things also. So at that time in the previous, at I don't know, it's maybe in 1950s or something. At that time, this simple model was able to capture all this, and people were able to study lot of things with this. Yes, vacuum. Vacuum. Yes, vacuum. Radios used to use that vacuum tubes. Yeah. So, okay. Yes. So it's famous. This equation is where anyone who tells this equation, they will tell the vacuum tube example first. That's the what that was very famous at that time. Now, if you have a second order equation like this, our basic methodology was like you take x dot is equal to some variable y, and so the x double dot will now become y dot, and you change all the terms to the right hand side, then it becomes minus nu times x will remain as x square minus 1, x dot is nothing but y minus x. So if you rearrange it, you can write it as 1 minus x square y minus x. So now this a and b has now become a first order equations. Now you can use our dynamical system equations to see how the curves will go. Yeah, please. Yeah, you were saying something? Yeah. Yeah, so there was a minus outside the nu, right? I multiplied it inside. Yeah, so that's just 1 minus x square. No, that nu is only with this minus is only up to this term. Not for this minus. This is plus x, it was there, no? In this one. Okay. So now once you have these two linear equations, now we will just I will just try to share the screen. Yeah. So if we go to the plane plotter and we just derived the equation, so it was like x dot is say some y and y dot was our say, so new value initially I give some value 1 into 1 minus x square minus x. So this was okay into y was that. So this was our equation. Now if you plot the phase plane, so we can draw that also. So if you plot that, so any point that starts over here, it will be eventually moving on to this kind of curved structure. So any point, so anywhere if you click, this point wherever it has started, it moves like this, and it will eventually goes to this curve, closed curve, which we are seeing here. So this, it's not a circle now, it's a distorted curve now, but it's a closed curve now. Similarly, anywhere you start, our system moves to this particular circle, not circle, particular closed curve. Now what happens if I increase the value more and more? You will see that the system, say I gave it as 3. Now your system, it gets more and more distorted and it moves on to the particular, still it goes to this closed curve itself. So anywhere it will eventually move from this and it will eventually move to this particular oscillation. So that's the distorted curve which we say in a van der Pol equation, and this is a unique stable limit cycle. It's an isolated because no curve near that is closed. You can see, say no curve near to this point is closed, only that particular point near to that is closed here, and all other curves are open, and any curve that starts here will go to this point, and whenever that starts outside also will try to come to this curve. So it's a stable limit cycle. So van der Pol equation has a unique and stable limit cycle. So that's what I wanted to show. So we will go back to this. Rayleigh-Bénard convection, it will show periodic oscillations. It will show limit cycle, it can show periodic oscillations actually, yes. It's a limit cycle, it shows a limit cycle oscillations or not, I just don't remember that now, but it will show periodic oscillation, that's true. It will show some dynamics up, then it will go down, then it will come up. That convection process makes it a periodic oscillation, that's true. Yes, a sine and cosine. If you take a, say if you have a sine like this, and if you convert it into a wheel and a crank like thing, this is basically like this is the point and it is moving like this. And if you draw the curve, it is actually it will come like this. If you track this motion of this particle over the circle, you will get a sinusoidal curve like this. So in order to, if you are not having any of the idea of the dynamics of the system and all, but you have some governing equations that governs that thing, you can use this nonlinear dynamics and say qualitatively, will the system behave a certain way, or is there anything that is going to come, also can be said using these things. But in late 1970s and 50s, people used for different other purposes. So in the next chapters we will see what something called chaos. So it's completely mixed up of a lot of things, and people use that for secret messages and all. So they will hide their message inside a particular noise frequency band, and on top of that they will put this chaos on top of that message, and they use this as a secret message sending technique and all they used to use. Yes, private messaging and all they used to do with this kind of things. So these are actually real-time applicability is there in all the tools which you are learning here. It depends on from system to system how to visualize these things and how to apply that. So in tutorial 1, which we will be seeing in the next class, I will try to explain certain examples till now what we have studied using these periodic oscillations and all. How we can visualize within a practical system, we will try to model it using MATLAB and all. We will try to see how the system behaves and all we will treat. I think that will help you in understanding more how to apply this. Yeah. Nu is, it's a parameter. When I was changing the nu value in the P plotter, it was changing its dynamics, but it is still a limit cycle. It was have a particular orbit around which all the curves were coming to that orbit itself. Oh, I varied nu at, okay, I will just show you once again. Yeah, I will show you once. No, it's fine. So we can, I will just put the value of new, say I will put initially 0 new value. I have kept, did you, are you able to, yeah. So initially I kept 0. Now when I click the point, it is circle. So this is the condition which I told. There is no damping term. It is completely x double dot plus x equal to 0 condition. Now if I slowly increase it to 1, now you will see that there is a small curve that is coming up, and all the points anywhere you start, this coming directly to that closed curve. So anywhere I click it, it's going to that particular point. Now if I move it to 3, now its curve length is increased, it's more distorted now. But now also any point that starts here, it eventually goes to this particular curve. And why we call it as a limit cycle? Because all the curves that starts outside, it goes to this curve, and anything that starts inside goes to this curve. Inside goes outside, and outside all come to this particular curve. Yeah, so that's why we call it as a stable limit cycle. So van der Pol is able to have a unique and stable limit cycle. Even if you change more and more values also, the curve becomes more and more distorted, but still it exhibits this particular curve. Orbit is closed and it exhibits a limit cycle oscillation. So there are, as you go up, people say that if you have entered into a limit cycle oscillation, it's very difficult for you to come outside of that oscillation. A system needs more energy, more effort to do that, to come out of that. So that's why certain systems, people don't want that kind of oscillations. So practically these kind of things are also, so people look into this from different perspective also. So yeah. Oh, okay. I don't know much about that. Sonar. Okay. You are saying that sound you are sending and it's reflecting back sonar. Okay. Yeah. How they apply there? They call auto oscillations. Oh, okay. Okay. Oh, okay. So you have seen such kind of oscillations. Oh, okay. Yeah, nice. Okay, so we just saw that we have closed orbits. Van der Pol is showing closed orbit and all. Now suppose by our suspicion, or say by numerical evidence, or any some other method, we are able to say that a particular system has, we want to say a particular system does not exhibit any periodic oscillation. Particular system does not exhibit any periodic oscillation or not. For that, we need to have certain criteria so that we can surely say, yes, this system will not exhibit any periodic oscillation. So we need justifications for that, to say that okay, this system will not have any periodic oscillation. We will have different theorems, or different people have found different systems which, based on certain system analysis and all, people have found out certain criteria. If you are able to meet those criteria, then you can say either the periodic oscillations exist or periodic oscillations never exist. So if you are able to say periodic oscillations never exist, then it's easy for you to tell, okay, my system will never go to oscillations, it is peaceful anywhere. And some cases, so there is some experimental setup called pulsed combustion. So where the pulse, the periodic oscillation, is what causes the power to be generated. So their oscillations are important. So people there try to see, do we get periodic oscillations? Whereas in particular cases, people say that you don't want periodic oscillations. So there is a requirement that we should be able to distinguish, will we have a periodic oscillation or will we not have any periodic oscillation. So for that there are certain rules that are being developed. So there are certain rules for testing closed orbits. Out of this, first method we will see is ruling out of closed orbits. It's like we want to say there never ever a closed orbit will exist in these kind of systems. We want to make such a statement. So for that there are different systems which people have classified. In that, first one is called a gradient system. So say suppose you have a system of a normal equation of the form x dot is equal to, so this is gradient of potential function. So I will just explain how it will end up. So if your system can be written in this form for some continuously differentiable, so it should be continuously differentiable, else its gradient will have a jumps and all, and it should be a single valued function. For this v of x. Then such a system, gradient system with potential function v. So such a system, that is the gradient system with a potential function v, will never have a closed orbit, or we say that closed orbits are impossible in a gradient system. So if you have a equation for a system, and if you are able to bring it to you can test this condition, x dot is equal to minus del v, if you are able to check, and if you are able to say that okay, my system shows this behavior or it is in this form, if it shows, then you can say that gradient system will never exhibit a closed orbit. Now we have made this statement, but how to prove it? So say this is our theorem which says that closed orbits will never have gradient systems will never have closed orbits. So how we will prove it is, so for that the proof is like, so suppose we consider there is a closed orbit. So to prove, suppose there is a closed orbit for a gradient system. If we consider like that, then it's a contradiction against what we are saying for the statement which we have made, but we will try to prove how it is and all. So if it's a gradient, Hamiltonian system like that, where you have del h, dou h by dou t, we are trying to see that. Sir. So here we will not go that, we will just say that initially say there is a closed orbit, and if we are able to contradict the value saying that there are closed orbits are impossible, and here we are initially saying that there is a closed orbit possible. So if we are able to get a contradiction among these two statements, then we can say that closed orbits will never be possible in a gradient system. So we will see how that is. So initially we consider, suppose there is no closed orbit. If there is a closed orbit, then the potential energy of that should be equal to 0, because we said that v is a single valued function. So since it's a single value, the del v of that will be equal to 0. Now this is the first, from our assumption that there is a closed orbit when we said, this is the first result we got. Now the second condition, this del v can also be found by like this. Say you have integral 0 to t or dv by dt. Sorry, this t dv by dt into dt. This is nothing but del v. We wrote it in an integral form. Now you can write this dv by dt can be written like this also. It's like dv by dx into dx by dt. So if we write that, we will write this as dv by dx into dx by dt into dt. Now dv by dx is nothing but gradient. So integral 0 to t, it's the gradient of v times x dot. Dx by dt is nothing but x dot into dt. And from the equation we know x dot is equal to minus del v is a gradient system. So if we substitute here, so 0 to t, we have del v is nothing but minus x dot into x dot into dt. So this is nothing but minus we take outside. This is nothing but a norm of x dot square dt. So this tells that del v is, if your delta x dot is equal to 0, then only your del v will become 0. So is that clear? So x dot, if it is 0, then only your del v will be 0. Yeah. Yeah. So this gradient system definition is this, that x dot is equal to minus gradient of v, and we have gradient of v here and we substituted that over here. Already you have one x dot here, so 2x, that's why it became square. Okay. Yes, minus is coming from the nabla thing, from the gradient system definition it's come. So now this means that okay, minus will come to the x dot thing. Now here we have only del v, sorry, x dot square, and the minus will come out. That's same thing. Yeah. So for you to del v, that is the, since v is a single valued function, and for del v will should, if you want to be 0, the condition it should meet is this mod of x dot should be equal to 0, or that means x dot is equal to 0 condition you should meet. And from the previous all studies which you have done till now, if x dot is equal to 0 means it's a fixed point. So this now contradicts with our statement that if we have a closed orbit, then del v equal to 0 is the condition it should meet. And if we try to find the del v with using this method, we see that x dot is equal to 0, that is at the fixed point only the del v becomes 0. So this contradiction shows that closed orbits cannot exist in a gradient system. So we have made a contradiction now, that if you have a closed orbit, then del v should be equal to 0, but we proved that if del v is equal to 0, then it should be a fixed point. So these two contradicts now. So that means you can say that, you can't say that there will be a fixed point or anything, but you can surely say that there cannot be any closed orbit. So that's the statement which we made. So closed orbits cannot exist in gradient system. So what is the use of finding this is, if you had a dynamical system equation and if you are able to write it in the form of x dot is equal to minus del v, and we know that if v is a single valued function, our potential function is if it's a single valued function, then you can say that my system will never have a closed orbit, or it will never exhibit a periodic oscillation. So by simply, yes, that's a condition. Yes. No. Now I will just give you one example to understand that. So say you had an equation of the form x dot is equal to sine y, and you had one more equation of the form y dot is equal to x cos y. So these are now two different equations which are coupled. Now we need to find, are there any closed orbits for this? So that's our question. So from the previous thing we know that from the previous studies, x dot is equal to f of x was our dynamical system equation, and from the potential function theory we know that f of x is nothing but minus dv by dx. Now we will take the first case, x dot is equal to sine y. If you take, this is nothing but equal to minus dv by dx. Now if you, so these two are our interested part now. So that means minus dv is equal minus dv by dx. Okay, since I am taking x dot here, I am putting minus dv by dx. If I take y dot, then minus dv by dy it should be. So if it is that case, so minus dv is nothing but sine y into dx. This I cross multiply. Now you integrate them. So minus dv is nothing but minus v, and sine y is a constant because your derivative is dx. So sine y will come out and you will have x. So your potential function v is nothing but minus x sine y. So now you got the potential function. V is now a function of x and y. Now we will check the condition. Can we write x dot, which is nothing but minus dou v by dou x, and y dot is nothing but minus dou v by dou y. So we want to write x dot is nothing but minus del of v, which is nothing but dou v by dou x plus dou v by dou y. Yeah, so if you are able to make this form, then you can say that it's a gradient system. So we will check for this now. So v is nothing but minus x sine y we have. Now dou v by dou x if you put, so it's like sine is constant and minus sine y, and dou v by dou y if you do, it's nothing but minus x remains in, sine x is nothing but cos y. So it's nothing but, yeah, so sorry, sine derivative minus you will get, then it will become plus x cos y. So the potential function v minus x sine y, you can say that there is a potential function v of x comma y is there, and we can write x dot is equal to minus del v form, we can write that. So we proved that there is a v like that for this system, and we proved that it's a gradient because this condition is met now. That means this system will never have a closed orbit. So that's the application how you can. So if now you don't need to know any of the theories, you can just check if you are able to write it as a potential. So if you remember, you might have learned this in fluid mechanics, stream function, potential function and all. Something similar to that is this kind of thing. there you find the gradient of the stream function to say how their vector field goes and all. Similar to that, if you are able to say there is a potential function existing, and if that gradient of that is equal to the x dot, if you are able to show, then it's a gradient system, and you can say strongly that you can never have a closed orbit. So that's the statement which we are able to make. And okay, so I will just cover one more small topic. So now you were able to say potential function and all. Now if you don't have this kind of potential function like thing, or you are not explicitly able to say this, and say we have in usual thing is every system has energy. So if some energy like function, if you are able to define, with this can we say will the system have any closed orbit or not? That's our next question. So if you don't have a potential function explicitly, we are not able to derive and all. So if you have certain energy like functions, can we use that to study will the system have any closed orbit or not? So that's our next aim. So for that, so I will just take a example of say non-linear yeah. Yes, contradiction, yeah, we can do like that. And so if you are not able to derive certain potential function for that, say in a nonlinear damped oscillator condition, say the same equation which you said, x double dot plus x dot cube plus x equal to 0, if you have certain equation of this form, and you are now not able to define clearly what is the potential function and all for the system, but we know that energy of a system is nothing but the summation of potential energy and the kinetic energy. So this energy function we know, x dot square. X dot square we got from the half m, v potential function is nothing but half m square, half x dot square. Yeah, p, same thing. So this is standard for every system. Now over a one cycle, if this x and x dot, they return to their starting values itself, then the net energy change will be 0. If they start with some energy and they come back to the same energy level, then the net energy will be 0 around a closed orbit. So if you have a closed, x dot is, yeah, x dot is 0, then it's a fixed point, it's not a closed orbit. Yes, same thing, same, x dot is equal to 0 if you are getting, then it's a fixed point. So if your delta E is equal to 0, then it should be around any closed orbit. Now same as you said, same conditions if you apply and all, what we want to say is like, say you have a function x dot is equal to f of x with a fixed point at x star you have, and suppose that we find some energy like function like this, we find a energy like function, not exactly energy if you, because in a complicated system it will be difficult to find. So if in an energy like function, so we term this energy like function as Lyapunov function. So if we are able to find some Lyapunov function for a given system, yes, function decreases along the trajectory and at the apart from the fixed point, anywhere the function will try to decay to that fixed point. That's the, so if you are able to define any Lyapunov function that is an energy like function, such that it is a continuously differentiable. It should be continuously differentiable. Then only it will be able to go down or move smoothly along a potential function, and it should be a real valued function. It can't be any complex number. And if these conditions are met, then that potential or that Lyapunov function v of x, which we say, it should be greater than 0 for all x not equal to x star. Apart from, so I will just draw the diagram first, then you will understand it more clearly. So this is, say, that v of x which we are saying. This is the fixed point, that is x star, and the function which you have found, that is the Lyapunov function which you have found, it should be greater than 0 for all x apart from this x star. That is, it should have a potential value. If it is staying here, it should have some potential value. It should have potential value here. At this x star only, it should have the least potential. That is, at v of x fixed point, it should be equal to 0. Then only it will try to come to this, because every system will try to minimize its energy. So any point, if it is standing here, it will try to come to this fixed point. And the second condition is the velocity or the time derivative of that v dot should be less than 0 for all x not equal to x star. This condition ensures that anywhere you start, it eventually tries to come down. That negative sign v dot less than 0 indicates that any point on the Lyapunov function, if you start, it will eventually come down to a stable point. So that means if your system is having some Lyapunov function, then you can say that your system will not have any closed orbit, because it will eventually come, it will oscillate, and it will not oscillate, it will eventually come to that stable fixed point. So this is one more method to say that there will never be any closed orbits present if your system is having any Lyapunov function. So in order to find a Lyapunov function, I will just finish this by an example. Say you have an equation of the form x dot is equal to minus x plus 4y, and you have an equation of the form y dot is equal to minus x minus y cube. Now the question is, does this system has any closed orbit? And they are asking us to construct a Lyapunov function. So the biggest limitation of this method is that finding a Lyapunov function, you don't have any standard rule to find that Lyapunov function. You try to do a trial and error method to find this Lyapunov function. Usually we can do, yes, so that sum of square is the simplest or the easiest way that works for this Lyapunov function. It's not a derived one, it's the one that works actually for most of the systems, but it's not derived from any principles or anything. So you can just take the sum of squares of the variables, say x square plus a y square we took here, where a is the parameter to be chosen. A we will choose, we will see how to choose a values. So sum of squares if you take as the Lyapunov function, usually this sum of squares matches with most of the systems. It is able to explain most of the systems, but it is not proved from any basic principles. That's why Lyapunov function is, getting the Lyapunov function for every system is difficult. But if most of the thing, this sum of squares will work. So if you have sum of squares, say v of x is equal to x square plus a y square, if you define, we will find the v dot value. So we need to do is just check these two conditions. If this both work, then you can say Lyapunov function exists for this system, and you can say there are no closed orbits. So that's our motive. So for that, first we will find the value of v dot. So if you differentiate this equation, you will get 2x x dot plus a into 2y dot. Now since we know what is the value of x dot is nothing but minus x plus 4y plus a into 2y times minus x minus y cube. So we can expand that and we will, so if we expand, I will just expand it, minus 2x square plus 8xy minus 2axy minus 2ay to the power 4. Now if I choose a value of a equal to 4, what happens is I can remove this xy term over here. So this xy term will go and I will remain with only minus 2x square minus 8y to the power 4. Now if we look on this, v dot apart from x equal to x star, it should be less than 0 was our condition. So for this equation, x comma y equal to 0 comma 0 is a fixed point. That you can find by directly putting it equal to 0 and you can determine the value. So x comma y equal to 0 0 is a fixed point. Apart from this fixed point, if v dot is less than 0, then we can say there is a Lyapunov function existing. So if you put that apart from, sorry, it's not a fixed point, but you have a potential function, sorry, Lyapunov function existing for the system, which says that you can't have any closed orbit. That was our main question. V greater than 0 or V less than 0? Yeah. Yeah, so V should be greater than 0 apart from anywhere x equal to x star. That's the Lyapunov function condition, no? Because anywhere, this is the minimum energy point. Anywhere apart from this, it should have certain energy value. And energy cannot be negative. It should have some positive energies only. Then only it can come to this 0 state. So anywhere apart from this x equal to x star point you are standing, your potential value or the Lyapunov function value will be greater than 0. But your v dot, that is your derivative of that, should be negative. Then only it will come down to this point. So you should meet both the criteria. So first criteria is at x and y not equal to 0 and x and y are positive. You can't take negative values in this condition. If you take, then both are negative. So initially v dot will be eventually will be less than 0. Now if you integrate this v dot, minus 2x square and minus 8y square separately, if you integrate, you will come down to x square plus 4y square you will come. So, or you take this and you can put the derivative. So this v is what we as assumed. Sum of squares we just wrote x square plus ay square, and v is nothing but 4 we have taken. So this is the potential function or the Lyapunov function. Now this v is greater than 0 anywhere apart from x not equal to 0 comma 0. X and y are positive every time, and apart from 0 comma 0 they are every time greater than 0. So v greater than 0 and v dot less than 0 apart from x not equal to x star condition is met. So that means you have a Lyapunov function being defined, and you can strongly say that there are no closed orbits. So that was our question, to find will the system have any closed orbits, and we proved that no, the system will never have any closed orbits. So I will just stop here. So there are two more methods to say there are no closed orbits, and we will have some famous theorem called Poincare-Bendixson theorem. So these three are important. So I will just cover this in the next session first, and then we will go to the tutorial one. Yeah, so are there any questions or anything? Yes, yes, dual X criteria and Leonard systems are there. Yes. Okay, so you are collecting back all the. Nice. Okay. Oh, okay. Oh, 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 okay. So Malavika, you were able to understand? Okay. So we will meet on Tuesday with the next session, and in that, yeah. Oh, okay, okay. Oh, next week you are having exam. Okay. Then I will put the next week complete. You will be busy or till Friday you will have. Okay. So okay, Saturday we have our group meeting. So then 5th December we can fix that. Week after that. Is it fine for you, Joe? Okay. Okay. Upcoming Tuesday you have some work. Oh, okay, okay. So 5th is fine. So then we will fix on 5th. 5th December we will fix. We will do the next session. Yeah. So all the best for your exam. Okay. Yeah. So then we will. Yeah. Okay. Thank you. We'll stop the session here. Good night. Okay.